Just while you do, I get a message sharing is paused. Can you actually see my screen?
I can see your screen. Yeah, maybe you can click the next slide and see if it works.
Yeah, it's on the first slide now.
No, it's still the title slide.
Right. Okay, let me just try something else then.
The recording is now running, so this is going to be tagged on, unfortunately. Maybe Alex will crop it for us.
How about this?
I can see the first slide and the title slide. Yeah.
Right, good.
Okay, great. Thanks very much, everyone, for coming. This is the first seminar of the semester, and our speaker is a celebrity guest, but no stranger to these lands, Sascha Troscheit, who actually is in St Andrews at the moment, which is rather ironic, but nevertheless, we're going to host him online. So, Sascha, thanks very much for visiting. Thanks very much for agreeing to give a talk, and over to you.
Right, thanks, John. Thanks for inviting me to speak. It's quite odd. Normally, I would say, oh, it's nice to be speaking here, but not actually be here. But well, I am, so that's a bit confusing. Even I'm in the old office, which is even more confusing. I've never given a talk from here. Anyway, so I'm going to talk about some things that I may have even started when I was here, but I doubt it. It was mostly the years after, when I was introduced to some random metric spaces that are more used in conformal field theory. And I applied good old dimension theory to it. So let me just, well, I know most of you are familiar with dimension theory, so I'll breeze through this a bit quicker than usual. Just to recap, and maybe also later set a bit of notation, just as the kind of basics. So dimension theory, well, the study of sets, measures with various so-called dimensions. And these are usually defined in some way to capture some sort of behavior, mostly geometric behavior of the set or measure that you're looking at. So for example, the Hausdorff dimension, it captures this the scaling of this efficient covering of a set. Whereas for the box counting dimension or Minkowski dimension, what you're looking at is the, again, a covering or packing, but with the same sized sets. So you're covering it all with some sets, but all of these have roughly the same diameter, for example. And for the packing dimension, you study packings. And the Assouad dimensions, which you've also probably heard about, do the capture the maximal locals, or the extremal local scaling, be it either to look at sets which are very thick in some metric way or very sparse in some metric way. And many others have been studied, and I'll also mention some which are kind of the in-between dimensions, the spectrum. But most of the time I'll be talking about the upper Assouad dimension, the Assouad dimension, capturing this local thickness, this extreme behavior. And here's the proper definition. So you're just taking your set and you're covering your set. Actually, maybe you can see my mouse. So what you're doing is you take your set X, and what you're doing is you're covering a row ball with balls of size r, and you're counting how many of size little r you need to cover this row ball. And what you're trying to do is find the minimal exponent such that you can bound it with this local scaling. Or if you want to think of it in a different way, what you're really looking at is all these magnifications, weak tangents, really just zooming in and taking Hausdorff limits of these sets that you're seeing, and you're looking at the maximal dimension that you can get locally as well. Now, maybe a slight note here, I will also sometimes talk about unbounded spaces. And for these unbounded spaces, note that this row is not bounded above by anything. You can get still some reasonable notion for Assouad dimension for these unbounded spaces. All right, so that's some of the dimensions. Some pictures to bring the point home. So you have your set and you want to cover it, and maybe you want to cover it with some R balls at a certain scale. This is what you might be doing if you wanted to figure out the box counting dimension. You just cover it, count, and then you take smaller and smaller balls and see what happens. For the Assouad, well, we're also going to zoom in a bit. So let's say we take this ball, we zoom in and we rescale everything to some kind of unit size and try to cover that again with smaller balls and see how many of these rescaled, or many of these balls you need with the proper rescaling. Maybe take some other part and you zoom in, and maybe this looks a bit more one-dimensional. And perhaps this is the most complex kind of set that you're seeing, and maybe this set has dimension 1. All right, so this was the Assouad dimension, and you can play around with it a bit. So you can form, for example, this natural dual, which you just exchange some of the infima and suprema. And this is the lower dimension. And this lower Assouad dimension looks for the sparsest set. So instead of looking for the part of the set which was hardest to cover, which, so as in we take the minimal exponent such we can cover everything, we would look at all these centers balls where we could just cover it very easily. And so we look at the maximal exponent that we could get away with there. And we can play around a bit more. So for example, the box counting dimension can be expressed like this. There you would, well, you're not really looking at localized balls. So maybe you can just take a big ball and you're just looking at covering this with smaller sets. And this is very analogous to the Assouad dimension, but really this is also just an equivalent definition of the box counting dimension, just to see that, well, there is some relationship between the two. I should say this is the upper box counting dimension. And this kind of motivates the Assouad spectrum, which John introduced with Han Yu. And this looks a bit like this. So instead of now taking all possible balls, smaller balls, and covering something like we did for the Assouad, or just having this global set, what we could do is take a relationship between the two. In this case, the larger ball is r to the 1 over theta for some value theta. And we're now looking at covering smaller balls with smaller balls of some radius r with this, and we have this fixed ratio between the two. And this, at least in theory, would give us more information about it. And indeed it does.
Can I ask a question, Sascha?
Yeah, sure.
So I guess you've got, it's a typo or something, but what r to the 1 over theta is much smaller than r.
R to the 1 over theta is a lot smaller. Yes, they should be the exact other way around. Well, thank you.
Thanks.
So yeah, these two should be reversed. Or you take them to the power theta, I guess, if you want to play that way. But thanks for letting me know. So yeah. So, but the principles are the same. You want to have this fixed geometric ratio between the two. And if you take your theta to 0, what you'll end up with is the box counting dimension, because, well, this thing here, well, if theta goes to 0, well, it should be the other way around now, of course. But then these scales are a lot smaller than the original scale. So you're capturing this box counting dimension behavior. Whereas if it's close to 1, then it looks a bit more like the Assouad dimension, but it doesn't necessarily need to converge to the Assouad dimension. There's something in between of the quasi-Assouad dimension, and that's actually where it tends towards. But in most fractals in the wild, as published Merkin said at some point, these two coincide, so it doesn't really matter. But yeah, think of this as kind of interpolating between this box counting dimension and this Assouad dimension, and really interpolates if you are more liberal with your interpretation of how small these smaller balls are. And you just take some arbitrary function, theta, maybe some nice enough, maybe continuous function or increasing. So you have this kind of behavior that you get from the box counting dimension, and you get through this spectrum and maybe some other spectra with this arbitrary function, then end up with the Assouad dimension. And I'll come back to this in that this can give us information about the set, and also tell us something about something like a phase transition, a geometric phase transition of a set, where you see one behavior and then suddenly you see a different behavior for a certain function psi here. All right. So these are all related in some way. So the lower Assouad dimension, if you assume compact spaces, is a lower bound to the Hausdorff dimension, lower bound to the box counting dimension, lower bound to these theta dimension, lower bound to the Assouad. And these Assouad dimensions, both of these extreme also have nice metric properties or topological properties, and that you can think of it as, for instance, the finite Assouad dimension happens exactly when a space is doubling. And the lower one, the lower dimension is positive exactly when a set is uniformly perfect. As in that you will find in any not too spread out annulus, you will find another point. And this Assouad spectrum interpolates behind me and should give us this kind of intermediate behavior between the two. Okay, so much for dimension theory, I think. No, oh, there's more. Right, so right, so the Assouad dimension has an application for embedding theory, and this kind of relies on the fact that, well, all of these dimensions, or these common dimensions, are bi-Lipschitz invariants. So if you have some notion of dimension, and a bi-Lipschitz map, it should stay the same. These Minkowski and Hausdorff dimension average too much over the space, and that they can always consider the entire space. And this is a bit of a problem. So if you want to actually find a bi-Lipschitz map, it's not really a good indicator of being bi-Lipschitz embeddable. Mostly because, well, you can have these extreme local behaviors that are not captured at all by the Minkowski or Hausdorff dimension. So the Assouad dimension is a much better candidate there. And because of this, local sensitivity is a good indicator of bi-Lipschitz embeddability. But also it's not too weird of a notion, in that if you have a very nice regular space, like an Alphys regular space, then all of these dimensions still coincide. The Assouad dimension still is what it should be, as in the same as the Hausdorff dimension, Minkowski dimension, and so forth. All right, so you have this very local sensitivity. So you can clearly then take this as an indicator. If you have, for example, a set with a high Assouad dimension, then you know that you cannot bi-Lipschitz embed it into something of a low dimension, simply because it's bi-Lipschitz invariant. And you might ask yourself, well, is the opposite true? So if you know something about the Assouad dimension, do we know something about the maps or the space that we could bi-Lipschitz embed it into in, say, Euclidean space? And this is actually not quite true, sadly. So taking a set, well, knowledge about the Assouad dimension gives us something, but it's not as good as you might think. You don't get bi-Lipschitz, but you might have to do something which is called snowflaking, just taking this to an exponent which is possibly close to 1. So you have to be a bit more flexible about the dimension. You can, knowing the Assouad dimension directly, you can get bounds on all of these constants and the dimension that you can embed it into, but it's a bit more complicated. So there is a whole host of literature out there which gives you bounds on all of these constants and dimensions. And maybe as a counterexample, the Heisenberg group, and the discrete Heisenberg group, is 3-dimensional, looking at it as an unbounded set, but you cannot embed it into RD for any D by any bi-Lipschitz map, because of the local structure of how this Heisenberg group interacts with itself. So the snowflaking really is a necessary thing. All right, so maybe now that's enough dimension theory. Yes. Okay, so the other big thing I want to talk about is random metric spaces. So maybe the first example that you might encounter is something called Mandelbrot percolation. So what you do, you start with a unit cube in D dimension, let's say the unit square. You divide it into n by n by n by n and so forth bits. So here into 2 by 2 bits. And then you end up with these 4 squares, n to the d squares. And you want to eliminate them with the probability p, say, independently of the rest. And you will end up with 0 to 4 squares. And then once you have these squares, you divide them again into n by n bits and do this coin tossing with probability p again and again, and you decide which ones you keep and which ones you don't. And if you pick everything in the right way, there's a positive probability that something will survive. And this something surviving, this complex set that survives, that is kind of the result of this Mandelbrot percolation process, usually just called the Mandelbrot percolation set. And this is really one of the simplest examples of something which is stochastically self-similar. And you can do some dimension theory and throw that at it. And in particular, if you have enough probability, as in if the p is greater than 1 over n to the d, then almost surely, with positive probability, something will survive. And if you think about it a bit, actually, there's always positive probability then that something will get lost if p is not equal to 1, because just in the first stage, for example, you could just have had bad luck and nothing survives. But if the probability is greater than this critical value, 1 over n to the d, you have positive probability that this limit is non-empty, and almost surely, conditioned on non-extinction, the Hausdorff dimension and box counting dimension is given by this expression here. So it's log p n to the d over log n to the d. And you might note, well, if you take p very, very close to this critical value, you can make the Hausdorff dimension as small as possible. Okay, so that's the Hausdorff and box counting dimension dealt with. They can be as small as possible, depending just on this parameter. And at some point, John Fraser and we looked at this from the Assouad dimension point of view, so it had been studied before. And really, the Assouad dimension is D. Why is that? Well, for it to be this extremal, what you need to find is on local scale, something which is extremal. And the extremal case here is that everything survives for a certain few generations. And of course, Borel-Cantelli tells us that, well, somewhere we will have it surviving for 3 generations, and then something in all of these subcubes, and then for 4 generations, for 5 generations, and so forth. So if we zoom in into the right places, now randomly somewhere, you will find these very, very full cubes. And this is what the Assouad dimension tells us. It tells us that these big things, well, are in there somewhere, and they mean also means that the dimension is full because these cubes are getting fuller and fuller. And if you take a Hausdorff limit, maybe if you want to think about that way, the limit set of all of these will become the unit cube again. What you can also then do is maybe look at all projections simultaneously into orthogonal projections into RK, and you'll get the same result. This is really just a very quick proof by the dimension theoretical properties of the Assouad dimension. But again, you'll see that almost surely you have simultaneously for all projections have full dimension. So this Assouad dimension really sees this extreme case everywhere. And looking at the Assouad spectrum, where you had this geometric relationship between them, you will find that this is not enough. Because on geometric ratios, you will not see this keeping all full subcubes for several generations is very, very rare behavior. What you need to do is to change this function to something where this either goes to 0 or infinity, and that tells you this is kind of the phase transition. This is the threshold at which point you will be able to see these full boxes, or where you won't. And if you don't see these full boxes, you'll always revert to this this formula here, log Pn over n to the d over log nd, this box counting dimension behavior. So this kind of is this phase transition for this random model. All right, questions so far? If not, I'll continue. So the probability, especially in geometric probability, kind of a question is generic. I mean, this is a very vague question, but what is a generic function? What is a generic tree? What is a generic graph? And coming up with models to describe these generic functions, for example, Brownian motion, and studying them really is a mainstay of probability theory. And you might want to think about, well, what is a generic tree? Well, several definitions might come to mind. Well, you could go for just a Galton-Watson process, but it looks fairly regular. So maybe you want to do a Galton-Watson process, and where you decide how many descendants you will have from one generation to the next. You build up this tree in a way that's maybe not as predictable, so critical, meaning that on average, you will have the same number of descendants as or sub vertices of your tree than you had before. And if you do this process and you condition on cardinality n, that might be a reasonable model for a generic tree. There's also this stick breaking model, which just comes from a completely different perspective. You just take a unit line, and with some nice stochastic process, you determine some point in there where you'll break this, where you will attach a new stick. So I'll take this stick, and you randomly decide another length, and then uniformly put it somewhere along this stick. So maybe you put it here, and then you take another random length, again from a nice process. I'm running out of props here. There's something here. And maybe you decided this is of this length, and then you uniformly decide where you'll stick it to this tree. And you build up a tree in this random fashion. Many other ways, and Aldo studied these generic trees, and for these definitions and many others, he showed that they are actually the same limit object, at least in distribution, if you look at from a nice perspective, like Gromov-Hausdorff distance within all compact spaces. And in fact, this is such a universal object that it merited 3 rather large papers by Aldous and then many others who have looked at the dimensional properties, but also just where in probability theory they crop up, what kind of properties they have. And one way which I find is the nicest way of imagining this is by gluing some functions. So this on top, this is really the definition, but really what we're just doing is we're taking the points from 0, 1 and putting a new metric on them. And this metric is given by a function on 0, 1. So you take an excursion function, it's just a function that starts at 0, 0 and goes to 1, 0, does something, let's say it's also continuous, and think of it as gluing the underside, sticking it all together, and then folding it out. What it means is that all of these peaks, which would not have seen glues in between them, they will fold out, and you'll get this kind of tree. Well, properly, you would define it like this, and you would really get a pseudometric space, but you just take out all the points that you've glued together, and you end up with a nice, proper metric space. And because you're also dealing with continuous functions, also a compact space that you're dealing with. So what would be a generic tree then? Well, you take in a generic excursion function. So you just take a Wiener process, as in you take the Brownian excursion, Wiener process that's conditioned on having exactly these properties, taking values 0 at 0 and 1, and being positive in between. And with this random excursion, this tree that we're getting out is called the Brownian continuum random tree, and it turns out to be a distribution equal to all the other ones that we've just talked about. So this is the generic tree. Now its Hausdorff dimension is 2, almost surely, and kind of also suggests that it has kind of 2-dimensional properties. Box count dimension is also 2. So looking at some process and trying to embed it, well, it tells us at least there shouldn't be too much distortion going on trying to embed it into R2. Right, so we could continue with this and talk about some other metric space. And actually, so really what I want to do is talk about 2 metric spaces. So I'm just continuing with one and the other, but bear this one in mind. So this is now this Brownian continuum random tree that we got from a Brownian excursion. And this is kind of the random tree as a good model for a random tree. All right, so if we want to talk about random metrics on the sphere, it's also a subject, and actually this has some applications, and I don't know anything really about them, but it is related to Liouville quantum gravity, which is a very important thing in common form of field theory as an invariant. But it turns out that the Brownian map, which I'm going to tell you about, is somewhat equivalent to this Liouville quantum gravity. And this Brownian map, what we're doing is we take other types of maps, other types of graphs, not trees, but planar maps on the unit sphere, and we place some n vertices make some planar map on them. Then we take this number of vertices to infinity. We somehow take a generic or random one of these maps, take n to infinity, and see what happens. Yeah, and so doing this in a nice, proper way, you will end up with something which is equivalent to Liouville quantum gravity. So you take quadrangulation, for example. So you take a map on the sphere where every face incident to exactly 4 edges. There is an edge case to this in that we would allow a vertex to be in the middle, and you have an edge just going to the vertex and have 2 sides. We'd count this edge essentially twice for both sides. And if you take these quadrangulations with n vertices, they are up to, with the graph metric, up to homeomorphism there. You can eliminate many of these. And really what you want to do is you take the Gromov-Hausdorff distance with this, you take more and more of these quadrangulations, you take n to infinity, you rescale the size properly by this factor here, 1/4, and 1/4, and this turns out to converge to some kind of limit object in distribution. And this limit object is called the Brownian map, sorry. All right, so you have this convergence, and it turns out, again, it is kind of a universal object. You can do this for triangulations, and they converge to that. You can do it for 2n angulations, and they converge to that. It's also assumed that it also happens for all the odd ones, 2n plus 1 angulations, but that's not proven yet. There are some complications in the proofs, apparently, but yeah, it seems like this is the limit object that you want to look at. And this Brownian map, essentially because you've built it up from the sphere, it is still homeomorphic to the sphere, but has a very high Hausdorff dimension, 4. So it looks very singular. And in fact, it's not really known whether there's a natural embedding. That's also what some people have tried to find, is whether there's a natural embedding of the Brownian map into the sphere. There certainly is a homomorphism. How regular can your map be? Because this Brownian map is a very abstract metric space, and a simpler description would be very nice to actually be able to study some of its properties. Okay, so this is what it looks like, at least for some large n, the largest n that my computer would do. And you see, well, it is still homeomorphic to the sphere. You can kind of arrange it. But because you have chosen random quadrangulation, some of these edges, well, there are no edges in between them. So really, these points are very far apart as a metric space in and of itself. So if you were to unwrap it and maybe try to display it in a more genuine way, then it looks a bit more like this. But because it's 4-dimensional, I mean, it might still look very nice and regular if we were to see it in 4 dimensions, but I can't do that. So it's still, the Hausdorff dimension being 4 implies somewhat regularity in it, and it implies that this object looks a bit more 4-dimensional, at least from the covering perspective. All right, but it turns out it is very highly irregular. So as you might expect, I was throwing the Assouad dimension at it. And the Brownian map, in fact, has infinite Assouad dimension. And moreover, you could also, okay, so because it has infinite Assouad dimension, you cannot map it into any doubling metric space because it's preserved. But really, you can also, from the proof, you can make it a bit more general by looking at other maps that you can do. And even snowflaking does not really work, because of some kind of structure that we find in there. And this structure is present both in the Brownian map, but also in the continuum random tree. And this structure implies that you cannot embed it into RD with any quasi-symmetric maps, so even a more fairly general notion. And given that quasi-symmetric maps and quasi-conformal maps are essentially the same thing in RD, it also tells you that while Liouville quantum gravity is conformally invariant, it still looks very bizarre from the Brownian map point of view, even though they are really the same thing. All right, so this is the main message. That's the theorem that I've put out there. But let me try and explain why this happens a bit more. And you, having studied or seen the Assouad dimension, you might think that it is because there's some very irregular, highly irregular local property. And yeah, you're right. But getting there is maybe not as straightforward. So to do that, let me just combine these two models, so the Brownian map and the continuum random tree, and tell you how to get from one to the other. And the way you go from one to the other from this tree that we have to a quadrangulation is with something called the Schäfer bijection, which gives you an explicit bijection between trees and quadrangulations. And the process looks a bit like this. You take a tree, you have a root somewhere, and you label it with 0. And then you label this tree in a way that the difference in labels between any two adjacent vertices is 1. So say this is 1, 2, 1 going 0, 0 here. The difference between all of them is 1. Once you've done this labeling, you stick an extra vertex in there somewhere, label it -1 or lower than your root. And you look at all the vertices that you have on your tree. I've highlighted kind of sectors. So these are all the sectors, these planar sectors in between the edges and the vertices. And you start at 0 and you draw for every one of these sectors, you draw a line to the vertex, the previous vertex that you've seen that has label exactly one lower. It's a bit of a mouthful, but this is what it does. You go around this tree, you connect the 0 with a label which is one lower, that's this one. You go along the tree, you go to the next label, that's 1. You connect it with one that's lower, that's 0. And you continue going around. And for every sector, you combine it with and draw an edge to the vertex that you've previously seen that had a label 1 lower. Now we get to the exciting bit. We've gone around here, we have this new sector, and we have to combine, attach this 1 to somewhere. Well, what's the previous vertex that we've seen that has one edge label 1 lower? Well, it's all the way over there. And you continue doing this, going all the way around the tree until you reach the sector that you've already done. So this is the end. So we've done this process of connecting them all together. And what you have now is actually quadrangulation. Might not look like one, but it is a quadrangulation. So because we're on the sphere, let me just shift this one around a bit and redraw them slightly. What you'll end up is this. So if you check any face, you will see that there are exactly 4 edges adjacent to every face, including this kind of weird case where you have both sides of this we count as an edge. Of course, the outside, of course, is also part of the sphere and has 4 edges. All right, so this is how you can transition from a discrete tree to a quadrangulation on the sphere. And you might want to try and generalize this process and get something which is somehow it converges to something, so that we can either take larger and larger trees, or we can already take this continuum tree, this Brownian continuum random tree, and go from there to there. So what's the essence that we want to capture? Well, if you just look at this picture again, what we've done in the beginning, it's just we've taken this tree and we've put labels on it. But these labels were always in difference 1. So really what we've done here is we've taken a random walk on this tree and labeled them with a random walk. And that's the key idea. What we want to do is we want to label them with a random walk, and then we combine things that are on this route which have the same label, very close to the same label here. And the continuum version of that looks a bit scary and like this. What you do is heuristically, what you build is a Brownian motion on the tree. As you have this random object, you have a random tree, and along this tree, you go along these geodesics along the tree, and you let this Gaussian process run with it. And this Brownian process that you run with it along the trees, that gives you this new metric. And it turns out that if you define a Gaussian process by essentially defining what this covariance is, that uniquely defines the Gaussian process on the tree. And you can then essentially throw in the same metric. So I'm not going to go through these details, but there is a way of actually constructing this metric. But maybe observe that this metric looks very similar also to the metric that we use to generate the tree from an excursion function. You take these 2 values and you subtract the maximal value that you get in between them. All right, so what does it look like? So if you were to just have a tree like this, and you take your process along it, and you might want to say, okay, so this point here, let's say this point X and this point Y, how close are they along this metric? According to the original tree metric, we go to the root and we go back, and the distance that we've traveled here between them, that is the distance in this tree metric. But in this new Brownian map metric, what you're looking at is you follow this Gaussian process from X to Y, look at the lowest value that you reached in between, and you take the difference in these values and subtract the minimal. That is something, so this distance between this X and this Y is something positive, whatever it might be, because this value Z is lower than the value at Y and at Z. But if you take some other point, let's say S here, and maybe this point S, this Z of S, this function here is roughly the same as here. What this means is that between Y and X, you could perhaps go along this point because these will be glued together. So this might represent a shortcut to go to y, as opposed to going all the way over here. So this is really to highlight that it's actually quite a complicated space, because you could go from not just along one side and go there, but you could also go the other way and then take this gluing here to reach y. And in fact, this is not just the tree. The tree is this thing that splits off at uncountably many points everywhere, and there's a Gaussian process everywhere. So really knowing what connects to what and what is glued together is quite some serious business. So how do you prove anything? Or well, that we have this high Assouad dimension. Well, let's first go to the tree itself, because on the tree it's fairly easy. What we want to find is a space that has a central point and lots of points around it that are close to the central point, but far apart from each other, like twice the distance. So something that looks a bit like a star. Let's call it also starry. If a metric space has these n stars with n different kind of rays going off for infinitely many n. So we're looking at this space that has these locally dense kind of things that you still need a lot of covers for, because they are far apart from each other, but not to this central point. And if you have a starry space, you can easily show that it must have infinite Assouad dimension. It's not doubling. These stars are also invariant under quasi-conformal and quasi-symmetric mappings. So all of the things that we want to prove, we get by just showing that these exist almost surely, in these structures exist. All right, so for the continuum random tree, this is fairly straightforward. All we want to do is find something that looks like this on the right-hand side. So what you want to find is a structure that goes, well, up and down a bit, and then gets glued together so that you will actually see these peaks. So this is for 4 peaks. As this one, I think it's a 10 peaks approximation. So what you want to do is you want to say, okay, we have this Brownian motion and this Gaussian process. It takes this form, it goes around this fn zigzag function and doesn't stray too far away from it to preserve these ray properties. And it turns out that this is that it's also too difficult, because, well, if you have a Wiener process, with some basic probability theory, you can say, well, for any continuous function, given that you have an epsilon neighborhood of it, there exists positive probability that the Wiener process will be in this epsilon neighborhood of any continuous function starting at 0. And what we really only need here is that it has some positive probability. And we can then use this invariance of the Brownian motion under scaling, which is exactly this a half. So we just take the same kind of zigzags, we put them somewhere in this function, and we just take them small enough that we get this Wiener process following this infinitely often. And all of these give you the stars, and presto, we have the star behavior, and we can then get all the conclusions that we want from it. For the Brownian map, it's a bit more involved, because, well, you're already living on this tree. So you now, let's say we are on this tree, which has this property of having these infinitely many stars, which have as high number of these rays as you want. We now also need to make sure that there's an that this Gaussian that you define along this star has nice enough properties, and that they are all kind of going away from each other. And that's the tricky point. So I'm not going to give you any details here, but really you want to be able to give probability estimates on these Gaussian processes along these geodesics to say, okay, there's also some positive probability, which is also somewhat scale invariant. And you do this by looking at the probability that along these trees, you have a Gaussian which has this bias in it. And by having this bias, you can then say, well, if there's enough bias, then these points, so let's say the point y3 here and the point y2, must still be far enough from each other by just saying, okay, the Gaussian must be very much increasing on these lengths, and nothing in between can give you any shortcuts in that there's a small epsilon neighborhood along a straight line with a certain slope. So that in here, there could be something that actually creates a shortcut, but once you go far away from this point, there's no further shortcut, and these endpoints are still close to some central point, but far away from each other. And you get this starry behavior. All right, so I'm drawing to a close here. So let me just say that these exception probabilities are very, very low. And this is a very rough estimate because, well, what you need is for this Gaussian to follow a very restrictive function that it really doesn't want to follow along. And you do this both on the tree and then later on when you're gluing these Brownian maps together. And because it is such a low probability, it's of course a very, very sparse behavior, which is also why, well, it's not embeddable, but there are only few exceptions to this embeddability. So it might be interesting to see, well, how sparse are these exception regions exactly? And you might be able to say something with this generalized Assouad spectrum, that you can figure out this phase transition of what is the right scaling at which you see this dense behavior, or where it is just so infrequent that you ignore and go to this box counting dimension behavior. So, well, knowing this, maybe it is possible to actually quantify the regularity of these maps to embed it into the sphere. We know into 4 dimensions, or RD for any D. We know it can't be quasi-symmetric or quasi-conformal, but maybe there is a weaker notion that can be then given with these spectra and with these phase transitions. All right, I'm going to stop here. Thank you for your attention.
Thanks very much, Sascha. I'm sure everyone's clapping thunderously wherever they are situated at the moment, although I can't hear clapping in the room you're in.
I heard clapping.
Oh, okay. Yeah, that was clapping. It needs to be more thunderous. Okay, so thanks very much, Sascha. Does anyone have any questions? Please put them in the chat or unmute yourself and just ask directly, whatever you wish. Maybe I'll ask a question to get the ball rolling. So when you were introducing the Assouad spectrum, I was sort of hoping you were going to tell us new results about this threshold, but it seems you were just teasing.
I'm teasing you.
Well, what's your feeling? There's this common threshold that has appeared in your work and other, I'm thinking of Canadian work mostly. Could that threshold appear again here, or is that unlikely?
I don't think so. So looking at the bounds that I have, which of course are not sharp bounds, they're just some structure that I found, that seems to be wildly differing. Mostly because you don't have, so usually what you'd see is this kind of exponential behavior with some probability, and you take this probability, you have some low probability P, and you want this n, see this n times, you take P to the n. And this kind of then bumps out of the formula and goes out and gives you the threshold. But here you want this Gaussian to not just go to certain places, but also stay within a very tight margin, and that lowers the probability significantly. So I would not expect the same type of threshold.
Is that something you want to do to work out what the threshold is?
Yeah. But yeah, so far the only thing that I did was look at the bounds that I had and actually show what they give, and they give something else. But of course, that's just the only thing that I found. But I find it very hard to believe that there's something much more efficient where you can find these very thick behaviors in the set.
Yeah, I mean, I guess for a time it was nice that this same threshold showed up in different situations, but now it would be nice to see a different threshold actually. So maybe a different one is what's going on here. Okay, any other questions?
This is maybe an elementary question. Well, it definitely is in context of this talk. Can you explain this picture that you've got at the end of your talk? These are the same object if you do some identification or something?
Say that again, sorry. Which
it was basically halfway through your talk where you explained how you kind of linked.
You mean the tree, the continuum tree?
Yeah.
What they were, yeah. I'll scroll back. Yeah, so all of these.
Yeah, that stuff. So, you had this picture of this Brownian, well, first you had this kind of curly graph, and you did some identification, and then you went straight to this Brownian thing.
Yeah. Yeah, so if you do this with Brownian motion, these are all the same limit object that you reach going, so looking at it from the Hausdorff metric, right? So you have them as abstract metric spaces, and you want to try and see whether how much alike they are. So you look at them in terms of a distribution. So looking at them in the space of all compact spaces with the Gromov-Hausdorff metric, they are the same object in distribution.
What I was, okay, maybe I've misunderstood everything. What I was confused by was the relationship between this. So in the next slide, right, you've got this wiggly graph there, and you go to the stick thing.
Yeah.
And then in the slide after that, you've got the bottom of this slide.
Right.
Right, you've got your Brownian motion, and then you go to this graph there. How should I think about that?
Right. So yeah. So this is so on this here in distribution. This is the same as, say, the stick breaking model or the Golden Watson properly rescaled, but it's also the same as taking your Brownian excursion and taking this new metric on it. So you put some glue underneath, stick it together, and fold it out, and then you will get something that looks like this.
Yeah. So what is the gluing?
Oh, the gluing is taking exactly this map.
Ah, fine. Fine. Okay, sorry. I somehow thought the colors that you'd drawn on the.
Right. No, they were just for illustrative purposes, not for confusing
right.
purposes.
Sorry.
Hopefully.
Okay, that makes sense. Thank you.
You explained it last time with this wonderful idea of glue. I think you said it this time too. Maybe you just said it there, I think. But this, like, you just put glue on like the underside of the graph, and then you just go, and then unfold it, and that's what you get. Yeah,
I didn't mention the colors, but yeah, that was supposed to be because all of these get identified. All the green ones, all the orange ones get identified. But you think of it as one big pot of glue you put underneath, stick it all together, and then fold out what doesn't come apart. So, for example, this line and this line, they will stay together, and then the red, and this will make.
Yeah, I understood that one, and then since my mind trying to work out the complicated picture and the gluing.
Right.
Yeah.
Right.
Okay.
You just need more glue.
Yeah.
Okay. Any other questions for Sascha? What sort of, I mean, you hinted at this question already too, but what if you can't do it with a quasi-symmetric embedding, but you can do it with a homeomorphism? I mean, what sort of families of maps should I even imagine in between those two?
Hölder, you could imagine, but Hölder's a bit much, I'd say. So this is just given by the Assouad embedding.
But
already.
You said snowflaking doesn't work. So,
oh no, sorry. Yes, no. It's then it's totally not possible. No, I was thinking of the Mandelbrot percolation for some reason. Yeah. No, Hölder doesn't work. But really, in looking at these common classes, I don't think there's anything that one commonly considers. That's also kind of the problem. Well, maybe the Assouad spectrum or this generalized spectrum tells you something about invariance or some embeddability in some function class, but whether that's a known class, I don't think so. But yeah, that's, I guess, the holy grail, right? To find a good application for embeddability of the spectra.
Yeah.
Nope.
Final questions? Okay, well, in that case, let's thank Sascha again. And hopefully, since Sascha's actually in St Andrews, some people might actually be able to see him and maybe ask him some more questions in person. But for now, let's end the seminar. So thanks very much, everyone.
Thank you.